Hello, my name is Bill Kinney, and this is the first of what I hope will be many videos on doing challenge problems from multivariable calculus. I often teach multivariable calculus, and here in early 2018, I'm teaching it out of this book, the third edition of Calculus, Multivariable Calculus by John Rogawski and Colin Adams. And most of the problems that I do probably will be taken from that book. I do find it to be a good book as far as its explanations, its graphical and conceptual insights, and it's got a lot of good challenge problems. These are problems that I often will be assigning to my students in multivariable calculus. I am focused on the problem-solving process in these videos. I know that I want from my students that they also write up their answers in complete sentences with appropriate diagrams like the one that you see here. I'm also making this available on YouTube for people around the world in case you are somebody who's interested in understanding how to solve problems from multivariable calculus. I think it's a very beautiful subject. I like it a lot, and I hope that beauty comes across to you, and I praise God with my whole heart for all the beautiful things that I have seen, and hopefully we will see together as we move through these problems in multivariable calculus. I will also make use of Mathematica to make these ideas and these pictures more real, more visual, more interactive, dynamic, you might say. You don't have to have Mathematica to appreciate what you're going to see. I will show you my Mathematica code in case you happen to have Mathematica and are interested in learning more about it. But it's something you can just appreciate without understanding Mathematica as a way to help us understand what's going on with these problems. And I'm usually going to do the Mathematica simulations near the beginning of the videos, and I will in this video, and then we'll get on to solving the problem after we look at what we see in Mathematica. So with the problem statement that you can see here in problem 11.1.66, which really means problem 66 in section 11.1, is that we've got a ladder. This black line is the ladder. It's 10 feet long. We're using non-metric units here, but let's go ahead and go with it here. It's sliding down a wall, so this is a wall over here. The y-axis represents the wall. As its bottom B that you see down here is pulled away from the wall. So you can see the arrows there in blue. The ladder is sliding. As time goes by, it's going to look more and more like this. Okay? It's going to get flatter and flatter because it's sliding down the wall. A slides down the wall as B slides across the floor. It's evidently kind of a slippery floor. We want to use the angle theta as a parameter. Now, what's a parameter? It's just another variable, x and y. The x and y coordinates of these 3 points, A, B, and P, are going to depend on theta. Using that angle theta as a parameter, find parametric equations for the path followed by those 3 points. The top of the ladder A, the bottom of the ladder B, and the point P that is 4 feet. This distance is 4 feet from the top of the ladder. Okay? Ultimately also show that P, as this ladder moves along an ellipse. And the ellipse was helpfully drawn in there in the book in the way that I've shown you right here. Okay, an ellipse is an oval kind of shape. It's not just any old oval, it's got to satisfy a certain equation, and we'll get to that here. All right, I'm going to go on to the Mathematica right now, and then we'll come back to the problem itself. So what you see here is the Mathematica file called a Mathematica notebook, in which I'm going to show you pictures, static pictures, and animations of diagrams that we look at in the problems we do for multivariable calculus. Again, this first video being on this sliding ladder problem, number 66. You're going to see that in coming videos, I'm going to do number 76 in the same section and number 79, tangent to a cycloid intersecting a rolling circle, and a rational parametrization of the unit circle, except for one point. You might wonder what that means. Anyway, I can open this section up and we can see some Mathematica code. If you're interested in looking at this Mathematica code, pausing the video, copying it down, whatever you want, that's fine. You don't have to understand what it means, but we're going to see what it produces. It produces the figure. This is the figure that we saw a short while ago on the piece of paper, showing us the situation for this problem. Again, it's made by this code that you see here. But now, in Mathematica, I can also make an animation of this, the key thing being this manipulate command to make the animation. And I can make an animation of what's going on with the ladder. So we see the ellipse here, the blue ellipse, a quarter ellipse, part of an oval. We see the point A up here, P here, and B down here. And we see an animation parameter theta. That is the angle that the ladder makes with the floor when you think of it as shown here. Okay, we can pause this at any spot that we want. We can see A, B, and P changing as the ladder moves down. Now this is not actually showing you how the ladder would literally move over time. Theta is not a time parameter, it's just an angular parameter. Probably what really happens in real life, you might guess, is that the ladder starts to move down faster and faster as time goes by. The point A over here, would move faster and faster. Since theta is the parameter, theta in this animation is changing at a constant rate. This angle down here is changing, decreasing at a constant rate in this picture here. But that's probably not what would happen in real life, okay? So you can see what's really going on here with this animation, and that's why I wanted to show you the Mathematica. Here is the code for the animation in case you want to write that down, but now we're going to go back to the sheet of paper and solve the problem. Although if you're interested, you can actually find the solution to the problem in the Mathematica code if you're familiar with Mathematica. Alright, we're back to the sheet of paper here and now trying to solve the problem. Again, the goal is to find the parametric equations for A, the top of the ladder, point A, B, the bottom of the ladder, point B, and C, the point P, located 4 feet from the top of the ladder, and also show that P describes an ellipse, or really part of an ellipse. Now the diagram is supposed to be really helpful, and if you didn't have this diagram, if it was just stated with words, well, you'd need more words than what you see here. You'd try to draw the diagram. And it's real important here to see that you can draw some triangles in here, and therefore you can use some trigonometry. So that's the key problem solving insight. If you draw this carefully, you can see there are a couple right triangles in this picture, here and here. We draw the right angles there. We also have this line that's crossing these two parallel lines, and therefore this angle, theta, right there, would be the same as this angle. This could also be labeled with a theta, like that, okay? And in each of these triangles, the 4 and the 6 represent the lengths of the hypotenuse. So this kind of picture and those kinds of labelings should quickly bring to mind, I hope, trigonometry, and in particular, SOH CAH TOA. That in a right triangle, the sine of the angle that you happen to be looking at, the non-right angle, is the opposite side divided by the hypotenuse, or really more technically, the length of the opposite side divided by the length of the hypotenuse. The cosine of the angle is the adjacent side divided by the hypotenuse, technically really the lengths of those sides. And the tangent of the angle is opposite over adjacent, the length of the opposite side divided by the length of the adjacent side with respect to the angle that you're looking at in that right triangle. So for example, if we look at this bigger right triangle down here, and let's say label this side A and this side B, then we can say, for example, that cosine of theta, looking at this bigger triangle here, is by CAH, adjacent over hypotenuse. For this right triangle here, for this angle right there, the adjacent side is A, and the hypotenuse, the long side, is 6. All right, so this A can be solved for now by multiplying both sides by 6. A is 6 cosine theta. We can also say the sine of this angle is opposite over hypotenuse. For this right triangle and this angle, the opposite side is got length b, and the hypotenuse again has length 6. So the sine of the angle is b over 6. And therefore, b is going to be 6 sine theta if I multiply both sides by 6. I can do something similar for the smaller triangle up there. Let me use a different color. Let's label this side right there C and this side D. Focusing on that smaller triangle and those labelings, I can say cosine of theta. It's the same angle, right? These angles are congruent. Cosine of theta based on this triangle and these letters is going to be, again, adjacent over hypotenuse. The adjacent side for this triangle and that angle is this side right there. It's got length C, so this is C over the hypotenuse length is 4. Therefore, C is 4 cos theta. And the sine of theta, based on this triangle, would be D over 4, opposite over hypotenuse, and therefore d is 4 sine theta. All right, is that helpful? If you think about it, it's very helpful. You think about the coordinates of capital A. Its first coordinate is 0. It's the point where the ladder is touching the wall. It stays on the wall. It stays on the y-axis here. Its first coordinate is always 0. Its second coordinate, based on this labeling, is the sum b plus d, which ultimately does depend on theta. We are then getting the coordinates of A as functions of theta. Theta is a parameter for those parametric equations, as they are called. What is that then? B plus D. Here's B, here's D. Combine those together. Add those together. B plus D is going to be 10 sine theta. So the coordinates of A, rectangular coordinates of A, are 0, 10 sine theta, and that would be a parameterization of the coordinates of A. What about the coordinates of B? Well, its first coordinate is A plus this distance here, which is the same as C. And its second coordinate is 0. B is a point that's always on the floor. A and C are 6 cosine theta and 4 cosine theta. Therefore, A plus C is 10 cosine theta, comma 0. And that's a parameterization of the coordinates of B. Finally, P is going to have first coordinate equal to C. You can see by this diagram here. The first coordinate of P is the x-coordinate. That's the distance C. And the second coordinate is B. I abuse notation a little bit here and say the point equals the coordinates. I can say it's C, comma, B. What is C? It's back there. It's 4 cosine theta. What is B? It's up here. It's 6 sine theta. And that's a parameterization of the coordinates of P. So we really answered that question. Find the parametric equations. I could write these in terms of x and y as well. Excuse me. For A, I could say x equals 0, y equals 10 sine theta as the parametric equations for the coordinates at the point A. I could also write them as an ordered pair like this. For the point B, at the bottom there, I can think of this as x, and this is y. X equals 10 cosine theta, y equals 0. Or I could write them as a point in ordered pair. Either way is okay. And for the point P, I can think of x as this and y as that. X is 4 cosine theta, y is 6 sine theta. What's the final thing to do? Again, show that P describes part of an ellipse. It follows this path that you see here. As the ladder slides, actually theta is decreasing. It's getting smaller as the ladder slides, as we saw in the Mathematica notebook. And that does mean P moves to the in the clockwise direction as theta decreases as the ladder slides down the wall. Why then is this a point on an ellipse? Well, you got to know some things about ellipses, and in particular, when they are in what's called standard position, the equation of an ellipse in standard position centered at the origin can be written in this kind of form, where capital A and capital B are unspecified positive numbers. Maybe you've learned that, maybe you haven't. Actually, I probably should not use capital A and capital B. I was trying to avoid the little a and little b, but I already have labels for capital A and capital B. All right, let's call them alpha and beta. Okay, that's going to go in the denominators of those fractions. What are alpha and what are beta? What is going to make this true? Can it be made true for this particular parameterization? Yes, you can think about it here. Alpha to be 4 and beta to be 6. Because if you take these equations and plug them in there for x and y, you're going to get 1 if alpha is 4 and beta 6, because 4 cosine theta over 4, quantity squared, plus 6 sine theta over 6, quantity squared, simplifies to cos squared theta plus sine squared theta which you should most definitely recall always equals 1, no matter what theta is. And therefore, we are satisfying an equation like this, an equation of an ellipse centered at the origin for some positive numbers, alpha and beta, in this case being 4 and 6. Actually, 4 is the x-intercept of the ellipse, and 6 is the y-intercept of the ellipse. And if you think about the values of these functions at the corresponding angles, that should make sense. For example, when theta is large, 90 degrees, when the ladder's straight up and down, cosine of 90 degrees is 0, and sine of 90 degrees is 1. So you get 0, 6. 6 times 1, that's the point right there, 0, 6. And then when theta is small, 0, when the ladder's on the ground, cosine of 0 is 1, sine of 0 is 0. This is a 0 there, just matching that 0 there. 4 cosine of 0 is 4 times 1 is 4, matches this point right there. This point is the point whose coordinates are 4, 0. Okay, so that's some extra confirmation that we've done the right thing. This is the best way to think about it, I think. And hope you got a lot out of that and enjoy the Mathematica animation. We'll continue doing problems like this with more Mathematica animations. But the key thing, again, is to think about the problem-solving process, think about the trigonometry that's necessary and the helpfulness of the diagram, and just what parametrizations really are. You're trying to get x and y in terms of some other number, in this case theta, the angle. It's often a time variable, t you might say, that is going to be our parameter in many of these problems. But in this case, it's the angular variable. And again, if you're one of my students, I now want you, if you have watched this video, to write up your solution in a nice way with complete sentences, with labeled diagrams. The key thing you're after is good explanations. Though ultimately, I hope you wean yourself from these videos if you are my student, so that you can ultimately also focus on problem solving, that you get inspiration from the way I solve things to help you become a better problem solver for future problems.